All right, I'll start sharing my screen now. All right. Okay, everybody, very good evening. Um, Welcome to the third live session of the course Essentials of Data Science with R Software, Probability and Statistical Inference. So, for those of you, if anybody is joining us for the first time, the idea is that we every week, 2 days before the assignment deadline, we would have these live sessions where it's assumed that you've taken a look at the course videos and if you have any doubts, you can ask those. We will take a quick look at what was taught that week. We'll practice some questions that would help you answer the assignment if you already haven't. In weeks where R would be discussed, we will also be discussing some R codes. And we will also be discussing any questions that you have with the previous week assignment in these live sessions. So each of these live sessions are going to be on Zoom. It's the fixed link. You will get a reminder every week, 1 day before the session. So on most weeks, it's going to be on Monday. If for any reason we cannot hold it on Mondays, you will get an email in advance telling you the exact date and time. Anyway, these sessions are going to be recorded as they're being recorded now. These recordings are going to be uploaded to YouTube. You will get the exact link for the videos um, as soon, like very soon after the class, and any material we discuss will also be uploaded on a Google Drive. Yes, I will share the link with you again. However, I'll just show you something here. Okay. So if you go on to, so you can see this page, right? This is your assignment, like the course page. So here at the bottom, you can take a look. You see this problem solving session, and here you see the recording tab. So if you open this, you'll be redirected to an Excel sheet which looks like this. So the Drive folder and your YouTube folder, like the YouTube link, all of that is going to be there. So you can access this directly. All right. So that should be all good. Yes, perfect. And so far we've had these two sessions for week 1 and week 2. And you've also submitted assignments for week 1 and week 2. So towards the end of today's class, we'll go to these assignments. And if you have any questions, confusions, sometimes grading and all might take some time. So I don't know if you've had this issue, but 1 or 2 questions in assignment number 2 have to be regraded, and the TAs who are dealing with the questions and the solutions know about it. But on NPTEL page, it takes some time to make those changes, like sync those changes. So even though right now you might have your score marked as 0, even if you answered correctly, wait a week. In case it's not sorted by then, I'll take a note of it again. But it should work out. It has worked out in the past also whenever there's any problem. So just hold on to that. But anyway, we'll take a look at it again at the end of today's class. So before we start, do you want to ask anything, discuss anything pertaining to this week or the previous weeks? You can, and again, as always, anytime you have any question, please feel free to unmute yourselves or write it in the chat box. All good? You can just give me a thumbs up. Yes. Okay. So assignment deadlines will not be extended and resubmission is not possible. Okay. So again, just for future reference, every Wednesday is going to be the deadline for submitting assignments. So if you are looking to getting a certificate for this course at the end, and if you are interested in giving that the final exam, uh, submitting assignments is very important. If you miss one assignment, it will not be a problem because as far as I know, they take the best, I think 10 out of 12 or something like that. So it should be okay. But just for reference, please remember that every Wednesdays you'll have assignment deadlines. The assignment deadline for week 1 and 2 were both together because people are still joining the course. But now, like, so today is the 10th of Feb. So day after tomorrow, 12th of Feb is the deadline for week 3. And so on, it's going to continue like that for each week. So you can just mark it in your calendars or just keep a note of it so that you don't miss it next time. 8 out of 12. Okay, that's better. Thank you. Thanks for the information. Yeah. So this information you can find on the NPTEL pages. And yeah. Okay. Cool. So if there are no more questions, I'll start. So we'll have a brief discussion on the topics taught this week, and then we'll solve lots of practice questions this time to make things clear. And yes, and then we'll take a look at week 1 and week 2 assignments at the end. All right. So, 1 second. Where did my pen go? Yeah, it's here. Okay. Fine. So we've seen in the past that this ohm symbol indicates that we are looking at the entire sample space. So the events that we are wanting to define is the actual entire sample space, right? So the probability of something happening, which definitely is going to happen, is going to be happening with a probability of 1. So that's a sure event. Probability is 1. And well, if you say you're rolling a dice, and you're saying what is the probability of getting a heads or a tails, well, that cannot happen. So that's going to be an impossible event, right? And you define an event, you get, so for event A, you get probability of A. And if you want to find the probability of A not happening, then you get what is known as the probability of not A, or the probability of complement of A. So that is denoted by both A bar and A with a superscript of C. Okay, both of them, they mean the same thing. All right, there's another term that you might come across, which is odds of an event. You might hear, maybe not exactly in this course, not in the next few weeks at least, but you might hear something like log odds ratio or odds ratio. So wherever the term odds ratio, something like that comes, so we are looking at a ratio. Okay, even though we don't explicitly say odds ratio here, we're talking about odds. So this is about something happening over something not happening. Okay, so probability of A, event A happening, and the probability of A not happening. So now what you can see, so if you just think about it very briefly, so both of them, we know both of them add up to 1. So that's for sure. Okay, one way to compare, so if both of them are equally likely, you'll say it's 0.5 and 0.5. If one of them is greater than the other, you say that's more probable than the other thing. So another way of doing that is taking a ratio. So if the probability of an event happening is higher, this ratio turns out to be 1. If the denominator is higher, then this ratio is going to be less than 1. It's going to be positive anyway, right? This ratio, so ratio of two positive numbers cannot be negative, and obviously probabilities are going to be positive. Probabilities are going to be between 0 and 1. So odds will be a positive number. If it's less than 1, you can say, well, event A happening is not very likely. And if it's greater than 1, you can say that the event A is quite likely. So that's just, these are terms that we will use later in the course, and these are just to make a note. Union intersections, well, of course, this is something, so if all of you have had Venns and probabilities, basically if you have had maths in 11th and 12th, you might already know this. But just for the sake of completion, we will quickly write all of that down just to know. So let's take a look at this using the Venn diagram. So you remember this is how we draw. Generally, a rectangle is used to indicate universal set. We don't know what it is, but it's still drawn. And then we draw these two circles to indicate events. Circle A and circle B to indicate events A and B. So now if you want to find the entire thing, okay, if you want to find out the whole space, so what happens is, so again, you can just see it visually. If you're taking A like that, okay, so blue here is indicating A, and if I just draw color B with a different circle, with a different color, let's say purple, you can see the center space is counted twice. So if you say A plus B, you're counting the center twice. So you just remove it once. And that is what we are doing here with the minus sign, this thing here. So we are counting it twice, but we are subtracting it one time. So now it's just counted once. So probability of union is probability of the like sum of the individual probabilities minus the intersection. And then of course you can rearrange this. So intersection goes to the left, union can come to the right, and then that's it. Right? So this is simple. This can be extrapolated when you want to work with 3 sets. So let's take a look at that. Let me draw a bigger rectangle or a square, whatever it turns out to be. So now again, let's draw these 3 circles. So A and B and C. So again, we are now, if you want the whole thing, so we have A and then we have B and then we have C. The problem still stays the same. We are counting. So now think about it. We have this region, we have this region, we have this region, and let's say so this is one type of region which is just common to 2 circles, and then we have this common region which is common to 3 circles, right? So when we did here, when we did A plus B plus C, we have counted this red areas. Of course, we have counted this twice, so we want to remove these. So we remove them, just like we did previously. However, we had it, so we had this thing once, so it's gotten removed once. We had this one extra time, removed it. We had this one extra time. Now this thing was in total thrice, and now we removed it thrice. So we are not even counting it once. So we add that one more time. We are adding the intersection of the 3 circles one more time. In the previous ones, it was 1 plus 1, so you remove 1. So you get 1. In this case, you had plus 3 and you did minus 3. So you lost the center part, so you added plus 1. Okay. So, so that's how these Venn diagrams work. All right. This is the basic. Of course, this can be extrapolated to 4 or 5. But typically, very, like usually you will see 2 and 3-way Venn diagrams very often. 4 ways are also there, not very commonly used. 5, 6, 7 people don't really use it. Okay. All right. Um, cool. So then next up, okay. What did I do? Okay. Anyway, so now, so let me know if okay. So basically, during in a couple of lectures in this week's like in a couple of lectures of this week, different examples were given, and some of them had something to do with permutation, some with combination, some talked about order being relevant or non-relevant, some being whether you're replacing the things or you're not replacing the things. So I've just made a simple, this is called a contingency table. The name is not very important, but this is just like a summary. So if you can remember this, maybe it'll help you answer those questions slightly better. So what happens here is, again, so we'll talk about these examples right now, and then depending on if you can identify whether order is important in something or not, or whether something's being replaced or not, you can talk about which of the 4 types of formulas are you going to use in that question. Okay, again, this is not supposed to be used blindly. You have to think about it, but this thing might help you a little bit. Okay. So, okay, so let's start. So suppose you're talking about, okay, I'm taking very general examples. The questions that you have in your assignment or even elsewhere, they can be a little bit more detailed. So directly this, so just remembering that, okay, winners in a lake follows this group, or team member select is about this group, not necessarily, okay? So um so we'll talk about that in a second. Like, okay, so don't blindly follow this, but we'll see. Okay, so example one, if you're talking about winners in a lake, winners in a race. So let's say 10 people are participating in a race, and you want to, let's say, choose you. So you want to get, what are the ways in which, like, what are the combination in which you can get the first three people who are winning the race. Okay, so remember we talked about one example last week, which dealt with replacement and non-replacement. So that was also the R code that we wrote using the sample function. Okay, anyway, the replacement and non-replacement thing means if something can be chosen again, then you are replacing it basically. So the example was that if you have a big bag which is full of different colored balls, and if you're, or maybe let's say these balls are numbered from 1 to 100, you selected one ball, let's say it was number 7, you took it out, and then you're choosing the next one. So you're not replacing the ball that you picked. So you cannot choose 7 again, right? So it is without replacement. On the other hand, if you took out that ball and you say, okay, that was number 7, and then you put it back in, shuffled it, and again pick another ball. Now, of course, you may get 7, you may not get 7. But that was with replacement because you replaced it, right? You could choose that same thing again. So that's the replacement non-replacement thing. And the order relevance or irrelevance, that is mainly, so suppose when you're saying you're choosing winners for something, if you're saying, okay, winner number 1, position 2, position 3, if that's what you're talking about, well, then order is important, right? But if you're saying, okay, we have 3 lucky winners and nobody's getting a better prize than the other, all 3 are lucky, then you're saying, okay, the order is not important. All right. So these are the two, mostly these are the two things you have to be careful about, because these things can make a lot of difference in how many options are relevant and non-relevant when you're calculating, right? Favorable outcomes, total outcomes, things like that. So when we're talking about winners in a race, if nothing has been explicitly mentioned, then typically something, so winners in a race would generally follow the order, right? So order is going to be relevant. Who comes at the first position, who's second, who's third, that's important, right? And a person who has come first cannot come second, right? So you're not replacing, you have to go without replacement. So in questions like those, permutation based solutions are what you would look for, right? So let's say example is there are 10 people who are running a race, and you want to know that you are declaring 3 winners, right? First, second, and third. So how many different combinations? So even if the question says combinations, don't get confused. So how many different ways are there in which people may be awarded winners, right? So can anybody tell me what would we do? You don't need to tell me the final answer. Just tell me the um formula. Oh, and by the way, yes, say that again. Hello.
So, ma'am, 10 into 9 into 8.
Huh? Yes, perfect. Okay. Yes. So just to make it clear, so whenever you write something like this, 10p3 for example, and you write 10c3, so here permutation is 10 factorial divided by 10 minus 3 factorial. So that's 7 factorial. And when you write combinations, you have 10 factorial, you have 7 factorial, and you have 3 factorial also. So for p, you have, so npm. So this is n factorial divided by n minus m. And here, again, the numerator is still the same. So the denominator is n minus m as well as m, both factorials. So for this question, as one of you rightly said, so it's going to be this thing. Now what happens is 10 into 9 into 8, and then you will have 7 factorial here. Denominator already is 7 factorial, so you can already cut this. Right? So you get 720 as the answer. Okay, cool. So does this make sense? Yeah. Okay. Now, I would like one of you to think about this. You don't need to necessarily, we are not dealing with actual cases here, but when you're fishing in a lake, okay, again, let's say you were fishing for whatever 15 minutes or maybe 2 hours you were fishing, and there were maybe 50 um like almost 50 almost catches, right? Like some fish got stuck to the hook, but you were not able to pick it. But finally, out of those 50, maybe 10 of them made into your bucket, right? So if you're looking at those 10 with respect to those 50 that you caught, are you talking about replacement? Are you talking about order? What do you think is happening here? Again, it's not a perfect question. It's just to give you a scenario. Like when you're finally looking at your bucket, does the order matter? Or can you catch a fish twice? Something like that.
I don't think the order doesn't, I mean, the order matters there.
Right, right, right. So the
Because
order
the
doesn't matter.
chances of missing the fish and getting it back in would be more at a point. So
Hmm.
order
So,
may
yes.
not be a big constraint over it.
Good, good, good. Correct. So again, let's not take the case where it's being replaced or not replaced, because again, let's say once a fish is almost caught, it's going to run away. It's going to swim away. Okay. So for the sake of discussion here, mostly you can assume it's going to be a without replacement thing, because once you've caught a fish, you've caught a fish. You can't catch one fish twice, right? That's a very rare scenario. So, and yes, like you said, order is not relevant. So, mostly it's going to be some sort of a combination based thing. Okay. So, yes, so something like that. So, you got 3 out of 10 fishes there, or maybe something like that. So, that would mostly be a combination based thing. So, if I just label it like this, if I call it A, B, C, and D, so mostly the winners thing would mostly fall into the the C category here. Fishing in a lake, uh, mostly it's going to be D, but again, not super important. And then when you are selecting team members, again, uh, there of course lots of ways are possible. Sometimes the same person can be given multiple duties, right? So replacement without replacement both can work, right? Suppose like you're making a team of 10 people, and mostly there's going to be president, vice president, and council heads, for example. So maybe one of the council heads is going to become the president, or maybe the council heads are going to be different, the president is going to be different. So that's like replacement and without replacement case. And definitely order is important there, because position, like whether you are the president or your council one head or your council number five's head, that matters, right? So such a case can fall into the category of A or C both, right? Again, we are not discussing exact examples here. These examples were discussed quite in detail in the videos. So if we discuss them again, it might consume a lot of the time and we might not be able to discuss more examples that are upcoming. So I hope this does not feel very empty right now. Okay. And then again, picking balls from the bag. We talked about it just a minute ago. So generally, order is not important when you're picking, um, unless you're giving it like first prize and second prize. Um, but again, this is very context dependent. So, but you can think about it. If you're replacing the ball that you selected, or you're not replacing the ball. Setting up an ATM pin. What do you think for that? Is the order important? Are we replacing numbers? Are we not replacing numbers?
We do replace numbers.
we do replace numbers. That's right. Because suppose your pin is 1, 2, 3, 4. It could also have been 1, 1, 1, 1, right? So when you used 1 in the first position, then it's not like you cannot use 1 for the next positions. So you are replacing it. You can reuse the same number. So yes, you are replacing it. So it's with replacement. And is the order relevant or not?
No, it is not. Because I
So
mean,
it
unless
isn't.
if it's it is,
Ah,
unless
it
we
is.
have a
It is.
constraint telling it's 4 pin or 6 pin, on that basis, yes, it is relevant.
Yes, it is. Because a password 1234 is very different from a password 4321. These are two different passwords, right? Two different pins.
Yes,
So
yes.
when we say order relevance, we are talking about, so again, yeah. So order is relevant in this case, right? Because these are two. So the way I sometimes think about order relevance and replacement thing is that so this setting up ATM pin thing fits both examples. So you can take this example, think about it, and then you would be sure of what these four categories are indicating. So typically setting up the ATM pin is category A, and then if there are no other constraints given in the question, then mostly so n to the power m, basically how many options you have. So you have 10 numbers and there are 4 positions that you have to fill. So it's going to be 10 to the power 4, right? So 10 into 10 into 10 into 10. This is generally how many ATM pins you can, like how many um, possible ATM pins there are in the world. Okay. All right. And then arranging 10 books in a shelf. So, of course, when you're arranging books, you are doing it without replacement because you can't put one book again. But so arranging 10 books, so maybe like, let's say there are two sub shelves that you want to fit them in or something like that. So if the order is important, mostly order would be important in these cases. So this would also be a C type of thing. But if the order is not important, um, it would be like a D category sort of thing. But yeah, so that's mostly what it is. Category B here, I realize I don't have an example for that. There was one, I don't know which it was, but there was one discussed in one of the lectures. This is a very, it's one of the rarer cases. So it's mostly going to be the other three. But yeah, just keep a mental note of the order irrelevant with replacement category. Okay. So yeah, so this contingency table might give you some idea on these are the broad 4 categories. Okay. So it should help a little bit. All right. Next up, we have conditional probability and Bayes theorem. So for those of you who, again, I think this was there in class 11th or 12th. So let's have a recap for this. So, um, so again, we talked about event A and B so far, right? We are drawing these circles. Now, suppose, what happened? Why is this not working? Uh, Oops. Give me a second. Oh, okay. So now, again, let's draw this example, A and B. So now if I just say that, okay, let me draw it a little differently. Okay, one more. So, oops, no, wait. Sorry. One more example. I'm just trying to draw it visually and I'm messing it up every time. Okay. Okay, better. Okay. Now, for example, let's say this is A and let's say this is B. Okay. Now, probability of A happening, whatever the probability is, okay, that's PA. Okay. Now, let's say I tell you that B has occurred. Okay. So suppose we can fill in numbers here 1, 2, 3, 4, 5, 6, 7, 8, 9. Suppose this is what these numbers are, right? You remember this is how we have defining sample spaces, right? Sample sets, sample spaces. So if I tell you, so probability of A happening, okay? So probability of A, well, it is, okay, let's say, whatever. Okay, now the thing is, probability of A, maybe there are a lot of numbers here which are left out. So 10, 11, 12, 13, 14, 15. Okay. Now, can you tell me what is the probability of A out of this? So the denominator is 15. How many options are we looking at right now? Favorable outcomes upon total outcomes, right? Hello? Can you
Is it
repeat? I could
4?
not. It's going to be 8 because you see the circle of.
Oh, yeah. Okay, okay. 8. Yeah, yeah.
Yes,
Sorry,
yes,
sorry.
8.
Yes.
Yeah. No, that's okay. No problem. The drawing is not doing justice, but yeah, okay. So suppose, so probability of A is 8 by 15. Okay. Now, again, can you also tell me what the probability of B is in this case? So B is 1, 2, 3, 4, 5. So 5 by 15.
It's 5. It's 5 by 15.
Right. Yes. So let's, for the sake of simplicity, let's call this roughly half. Let's call this roughly, like this is exactly 1/3. Okay. So now, if I tell you that B has occurred, if I already say that B has occurred, so you already know that you are dealing with numbers 5, 6, 7, 8, or 9. Okay. Now I'm asking you, now what is probability of A given that B has occurred? Okay. Yeah.
So on that
Oh,
note,
let's
4.
let's do something else. Wait, sorry. Let's call it just to, maybe this example was not the best I took. Sorry, just give me one more minute. Let's say if A has occurred. So when we say A has occurred, it means 1, 2, 3, 4, 5, 6, 7, and 8. And if I say what is B given A has occurred? Yes, sorry. Now you can continue. Or should I go ahead?
So you mean to ask a question that if A has occurred, what would be the probability of B?
Yes, yes. So earlier the probability of B was 1/3 when you're talking about the total set. But now we
Okay.
have extra information that A has occurred. So we know that, so for example, let's say this was a 15-faced dice that we are talking about, okay? So when you roll a dice, it's just one of these 15 outcomes. So if it was like when we rolled a dice, A, so event A is, let's say, favorite numbers of person 1, B is favorite numbers of person 2. Right? So this is what is the probability of person 1 getting their favorite numbers or person 2 getting one of their favorite numbers.
Is it 4 by 8?
Okay. I have not yet calculated it, so let's walk through it together. So now the idea is, okay, so A has occurred. So now you just have 8 of these options. So your effective sample size has reduced, right? Earlier we were talking about 15. So you see denominators were 15. Now the denominator basically, so again, it's not the exact way of writing it, but for argument's sake, so it's one of these 8 numbers now only, right? So A has occurred, so obviously numbers 9, 10, 11, 12, 13, 14, these are not there. That we know. So yes, so the effective sample size is now just 8. So now what is the probability that it's so from A we got these 8 numbers, and for B, so now B as such has 5, 6, 7, 8, 9. But of course we know 9 cannot happen. So now it's 5, 6, 7, 8. So it's 4 by 8.
So that
So
is
now it's
basically
half.
probability of A intersection B, right? As per the formula.
Yes.
So
Exactly,
it's
you're
4
right.
by 8. Okay.
Yes.
Got it.
So now, yes. So the idea is, so here we were looking at probability of B. Now we are looking at probability of B given A. In both cases, we are interested in the event B, but we have extra information about occurrence of A here. So what has happened? So of course, half is greater than 1/3, right? So, so this, the bottom line in this slide. So this extra information. So just give me one more second. What I'll do is, I'll just change this so that, because this is what we've discussed here. And again, okay, never mind. I think you'll be able to understand. So it works both ways. We could do it the other way around also. So, but generally what happens is, since you've got more information about something occurring, something non-occurring, in most cases you would see that the probability of something happening has increased. It's not going to always happen. Conditional probabilities can also decrease the probability. Okay, that is what was happening when I was initially drawing the circle different way. But anyway, so in this case, what is happening is that the effective sample size is reduced. So now you're talking about, so earlier you were talking about 5 out of 15 cases being favorable. Now you're talking about 4 out of 8 cases being favorable. Okay, because your effective sample size is reduced, right? Um, so, and this is the formula as one of you rightly pointed out. So you see here, so this is what we were looking at, right? Probability of B given A. So the denominator was probability of A. So now the denominator was actually 8 by 15 if you think about it. That 8 was happening because it was 8 by, this was actually 8 by 15. Should have just drawn it better. I'm really sorry for the messy drawing today. Yeah, so the denominator effectively is 8 by 15. And the numerator is actually A intersection B, as one of you said. So that's 4 out of 15. But since those 15 cancel out, it's effectively 4 by 8. But the right way to understand this is the formula that we are looking at in this example. B given A is intersection divided by the probability that you already know has happened. And likewise, you can do it the other way around. Probability of A given B. Again, intersection stays the same, but the denominator is the probability of the event that you already know has occurred. Now, if you have these two formulas, you can see the top right here, the numerator on the right on both cases is the same. So you can do a cross multiplication, you can equate these two cases. So A given B into B and B given A into A. You can equate these two. So you get this sort of a formula, which is not dealing with any intersections now. But if you have, so again, there are 4 things here. If you have 3 of these known to you, you can calculate the 4th. Okay. So that's what, so conditional probability is basically A given B or B given A. And this form of using that conditional probability is what is Bayes' theorem. All right, any questions about this? Okay, if not, then let's go to the next slide. Okay, yeah. So now this is again, okay, some formatting has gone haywire here. Give me 1 second. This needs to go in the superscript. I think that should be fine. Okay. Alrighty. Okay. So here in the previous example, we were just dealing with 2 events. But of course, we can deal with multiple events too. Okay. We can also deal with complement and non-complement. Okay. So let's take, so let's talk about the complement thing before, like first. What color do we use? Let's use this. Okay. So again, let's draw the same thing as the previous one. So let's say this is A, this is B. Now, again, we are talking about probability of B, right? So can we split the probability of B into two parts? Can we call this as part 1 and this we can call as part 2, right? Now, this case we can say that this is probability of B given A, right? Something like this has got something to do with that. Okay? And this is basically something to do with probability of B given A not happening. Isn't it? Right? Does this notation make sense? Just give me a thumbs up if it makes sense. If it doesn't, let me know it doesn't make sense. I hope you're still all online. Just give me a thumbs up. That would be enough. Or just say okay in the chat. Okay, I'll assume it's fine anyway. Okay? Yeah, okay, cool. Thanks. Alrighty. So, right, so we can, so we've basically split B into B, which is occurring along with A, and the rest of the B, which is occurring with A complement, right? Because you remember, everything outside of the whole circle of A is A complement. And this directly is not enough. B given A, B not given A does not add up to B. So you have to multiply it with the denominator, uh, the one which has occurred, as we saw in the previous slide. So this is the formula that you get, right? B given A with the probability of A, and B given A complement with the probability of A complement. Okay. So this is when you're talking about B and one more event. And if you're talking about multiple events, so I will not draw a Venn diagram in such a case, but what we can do is, let's just divide the grid like this. Let's say this is B, and let's call it A1, A2, A3, let's say some AN, then maybe call it AM, AI, AJ, AZ. Different numbers, okay? Now, B may not depend on everything, right? But B may depend on one of like some of these cases. So just an extrapolation of what we saw here. So probability of B given one of the cases, probability of B with some of the other cases, another, all such cases. The only thing is with the other possible cases, there would not be B happening. So if I say what is the probability of B given 3 has happened, you will say 0, because if A3 has happened, then B can't happen because B doesn't exist there. Okay. So again, these are formulas right now. We are not exactly talking about many use cases for these, but this larger example is just an extrapolation of the simpler thing, which I'm sure you are all understanding. Okay. All right. Let's head to the next slide then. I think, yeah, this is the last thing. All right. So this was another example that was discussed this week. Again, talking about conditional probabilities and Bayes theorem. Again, you're seeing this 2 by 2 table here, right? This is a slightly different 2 by 2 table. So before we go into the actual question, I'll just explain you what such cases talk about, because this is important not just when you're talking about Bayes theorem or not just about probability, but in general. Okay. So let's take the example of COVID-19. Okay. When the pandemic had started, there were no reliable tests. Okay. You would have, over these years, you have heard about the rapid antigen test, the RT-PCR test, maybe something else. Okay. So each of them, none of them are 100% perfect. And when we say perfect, the test needs to do two things right. If a person who actually has an infection takes the test should say the person has the infection. That's one of the things it should do. The other case it should do is if the person who actually does not have an infection takes the test should say negative. Okay. So there are two types of correct results that we're talking about. Okay. So if it's wrong in either side, if a positive person is detected as negative and if a negative person is detected as positive, they are both false results. They're not true results. Okay. So in this type of a scenario, positive and negative are not the terms you want to focus on, but rather true and false are the terms you want to focus on. Okay. So again, what this table is telling you is person with infection. Okay. So the ground truth, the truth which we don't necessarily know, that is a person has an infection. Okay. They take the test. If the test says you're positive, then that's a true positive. The outcome was positive. So again, the thing is, when you're taking a test, you don't know what the truth is. So this thing here, okay, the two columns that we are looking at, why is this stuck again? Okay, the two columns, these are generally known as the ground truth. Okay, this you don't always know. You assume. A lot of time this is assumed, but well, can't help it. And then these cases, that is what your outcome is. That is the outcome that you see, right? You see what the test is showing you. So the test says positive, and well, if somehow you actually knew the truth, you would say, yeah, that's a true positive. Okay, correct. Now, if the test says positive, but you actually know the person does not have infection, then you'll say, okay, it's a positive result, but it's a false positive result. Okay, that's where this term comes from. Likewise, if the test says negative, so you say it's a negative result, but if the person actually had the disease or the infection, then you'll say that's a false negative result. And the last case, the person actually did not have any infection or any disease, and the test also said so, then you'll say, yeah, that negative result is a true negative result. So these top left and bottom right are correct results, and the other two are false results. Okay, fine. This is one thing. So, yeah. So generally, this would be the scheme of things when a person is developing a test. So, for example, let's say there is already a good test available in the market for a particular disease. Okay. But let's say it's a very invasive test, it's very complicated, very expensive, blah, blah, blah. Somebody is developing a cheaper test, which can be done even in low resource settings. Okay. So, in that case, using the gold standard tests, you know the ground truth. And then you're testing your new, cheaper test. Okay. So in that case, there is already a lot of information known about the disease, known about the prevalence of the disease. So probability of the disease. So basically, you know how many people in a population suffer. So let's say the probability is 0.0001. Generally, this is what these are the kind of numbers you'll be dealing with, right? Mostly, these are not going to be super common diseases. So this is something like 0.01%. Okay. What you might also know. So again, these numbers don't need to be same. I can actually change this just to make it, let's say it's 0.9 or something. Okay. So, so let's say you do the test on people who have the disease, and let's say you do the test on people who don't have the disease, right? So T basically means positive test outcome on people who actually had the disease, and negative test outcome who did not have the disease. So these are both the true positive and the true negatives that you're dealing with. Okay. You would also have the other two values with you, but that you can always calculate, right? So just to be on the same page. What can you calculate from these values? So if I have probability of t given this and probability of this given this, what would these be and why? Yes. Okay. So now the thing is that this and this. So the event that has occurred is the disease not being there. So the infection is not there, the person is negative. When the person is negative, 0.9% of the cases, 0.9%, yeah, or rather 0.9, so 90% of the cases tell that the test was also negative, and for the rest of the cases, the test was actually positive. So event occurred, disease not being there. There are two possibilities. The test showing negative, test showing positive, they both have to add up to 1. So it's 0.9 and 0.1. Likewise, for the disease being there, for the person being diseased or infected, again there are two cases. Test being positive and test being negative. So the positive test is 0.999. So the negative test is 0.001. So basically, these are the 4 values you already know. Mostly 2 of these values are going to be known in the question. Prevalence of the disease would also be known in the question, because this is what the people have already done. Now the real question is, now if the test comes into the market and if you are using that test, and if somebody is using that test and they turn out to be positive, what is the chance that maybe you were actually not positive and maybe the test was wrong? Or maybe you tested negative, but what if you actually had the disease? Things like that. So now the ordering has changed. Now you're talking about having the disease given the test result. Okay. So this is what you would be interested in. And this is what the probability would look like. And I've written over it, but that's okay. So disease given the test outcome, you can use Bayes' theorem. You get this. And now the denominator can be split. We just saw this in the last slide. So the test outcome, whether or not, so assume this test outcome was A, event A, and the disease was that event B that we talked about. So, right, so it's going to look something like this. And now you can just plug in the values and that's it. Does this make sense? So it's not super difficult. It can look like a lot of numbers here and there, but these are not very difficult questions. Okay. Are we good so far? All right. So I'll assume it's all clear. So that is what was discussed this week. Now I have a lot of practice questions for you. So let's walk through them together. All right. So a committee of 5 is to be selected from a group of 6 men and 9 women. If the selection is made randomly, what is the probability that the committee consists of 3 men and 2 women? So what do you think? How do we go about it? So these are practice questions. So I am not going to directly answer them. One of you can start by leading the discussion and then we can work towards it together. You can put it in the chat also. But rather than going straight to the answer, it's more important how we, like, it's better if we start with the working. Okay, another thing that I don't know if we discussed this last week, but these terms and or, So yeah, we discussed this. So this is generally when we are dealing with intersections, and or is generally when we are dealing with unions, and is generally when we multiply, and or is generally when we add. Okay. Come on, this is not a very difficult question. One of you can please unmute yourselves and write. If it's clear, then I'll just skip the question, because it's better if we have a slight discussion on this. Anybody? Okay. All right. So quickly.
So it is 5.
Hmm. Sorry, say that again.
1 minute, 1 minute. Sorry.
Yes. No, no, that's okay. Take your time. So we have to select 5 people, right? And order is not
First, we
important.
have to find the total number of people.
Yes.
And so number of ways to select 3 men and 2 women
Uh-huh.
would be so it is
Okay. So,
62
huh?
and
63.
oh sorry 63 and
Huh?
9C2 if I'm not wrong.
Yes, perfect. Right.
Okay.
Yes. So basically 3 men from 6 men. So 6C3, because combinations, because we are dealing with combinations, because order is not important, right? And so the and here basically goes with this multiplication symbol, and 2 out of 9. So that's it. So this is simple. That's the answer. Okay, you can calculate this. So you know it's 6 factorial by 3 factorial by 3 factorial, 9 factorial by 7 factorial by 2 factorial. Of course, you can calculate this. You'll get the answer. Okay, so that's fine. Next, a coin is tossed twice. If we assume, okay, so coin is tossed twice, you have 4 options, right? So if you assume that all the 4 points in the sample space are equally likely, what is the conditional probability that both tosses result in heads, given the first toss result in head? Now, if you just need the answer, you can answer it. You don't need to necessarily go through the Bayes theorem formula. You can just type in, like, you can just write in the actual possibilities here. So, for example, your sample space is heads, heads, heads and tails, tails and heads. If any of you know the answer, you can already let me know, but I'll anyway show the working alongside. So again, if the event A that you're looking at is, this is the event, right? Both result in, this is there. This is what you are looking at. And let's say another event is the first tosses head. So that could be, oops, this and this, right? So what you want in this question is A given B, right? So there are 2 ways of doing it. You can simply say this is like 1 by 2, because this is 1 out of the 2 options. But if you want to elaborate, the other way is, like we said, A intersection B by probability of B. So A intersection B is obviously 1 out of 4. This is 1 out of 2. What did I do? Did I do it wrong? This is fine, right? Yeah, half. Yes, correct. Okay, that's it. So you get half anyway. Alrighty. Okay, another question, very similar to the last one. So an urn, which is, let's say it's just a pot, it contains 10 white, 5 yellow, and 10 black marbles. One marble is chosen at random from the urn, and it is noted that it is not one of the black marbles. What is the probability that it is yellow? Again, let's define two cases. Would any of you like to try before I actually give the answer? And rather than solving it independently, you can unmute yourselves and let us know what you're thinking. And so we can see how such a question has to be approached, because that's more important than finally calculating, because, well, you would have calculators. So that should not be a problem. Anybody up for this? No? Well, you've all
Give me
joined this
1 minute.
class.
Give me
Yes,
1 minute.
sorry. Okay, that's okay. Take your time. In the meantime, if anybody has any questions, you can pop that up, or we can wait.
So the total possible outcomes would be the sum of these three. That is 10 plus 5 plus 10, that is equal to 25. So
Correct.
we have that one of, I mean, the one which we take may not be the black, not one of the black marbles.
Mm-hmm.
So if that is the case, our the favorite outcomes would become we have to subtract 10 from that, so that becomes 15.
Correct.
So finally, the favorite outcome would be only 5 on a probability that the selection is going to be yellow.
Perfect.
So how would we calculate that is, so
Mm-hmm.
the total outcome would be 15 excluding black. So that would be 5 by 15.
Mm-hmm.
That would give you maybe 5 by 15 is like 1 by 3.
Correct.
So 0.33 would be the probability.
Perfect. Great. That's it. Right. So again, basically your sample size is reduced. So now you're, instead of dealing with 25 marbles, you're only dealing with 15 marbles. So earlier the probability was 5 out of 25 of it being yellow. Now it's 5 out of 15. Cool. Great. So that's how you have to write it. Again, we could also have written as 5 by 25 and 15 by 25, canceling 25. But again, this is how the answer is. Both the options are, both the ways of solving are correct. Okay. A barcode has 5 blue lines, 2 red lines, 3 black lines. Each ordering of 10 lines, so this is total 10. Each ordering of 10 lines represents a different barcode. How many barcodes can be generated? So this I'll just let you know, because we might not have discussed this explicitly. At least we have not discussed this in today's class. So I'll just let you know. So it's sort of like, so again, let's say I'm drawing these. Let me draw it with these colors now that I have the colors. Okay, so I have, let's say, 5 blue lines. I'll call them 1, 2, 3, 4, 5. And then I also have 2 red lines. Let me call them 1 and 2. And I also have 3 black lines. Okay, 1, 2, and 3. Now, suppose I jumble them up. Okay, it doesn't really matter if I'm placing my red number 1 somewhere and red number 2 somewhere else, or if I swap them. You can't identify one red from the other, right? So we have to remove those many cases, right? So the thing is that we have 10, um, we have 10 factorial barcodes, right? Because as per the simple case, as per that 2 by 2 table that we talked about, here we are replacing, we are not replacing, and the order is important, right? So if you remember, uh, without replacing order element, we do permutation. And in this case, we are selecting 10 out of 10, right? So it's basically 10p10. So that's 10 factorial divided by 0 factorial. And that is 1. So that is 10 factorial, right? But since these are repeats, there are some repetitions. We have not talked about repetitions here. When we have repetitions here, you have to remove those possibilities. Okay? So what you do is you have to remove all repetitions. So there were 5 repetitions here. So you remove by dividing it by 5 factorial. There were 2 repetitions here. You remove it by dividing by 2 factorial. Then you have 3 repetitions. So you remove it by dividing it with 3 repetitions. So this is what you get. Okay. So this is the final answer. Okay. Any questions about this? All right. Okay. So the probability that an instrument gets damaged due to high voltage or mishandling. So we're talking about two things: high voltage, mishandling. They are 0.3 and 0.4 respectively. The probability that an instrument gets damaged due to high voltage and or mishandling is 0.5. A damaged instrument is randomly picked up and inspected. What is the probability it is damaged due to high voltage as well as mishandling? Okay. Now this is a very simple question about the union and intersection formula. The main thing is you have to identify what is A, what is B, what is union, what is intersection, which of the 3 things are known, and which is the 4th thing that you have to calculate. Okay. So let's call A as high voltage. And let's call event B as damage due to mishandling. Okay. So what values do we know here? It's a very simple question. So maybe I'm taking more time on this, but this is important because you have got this term here and you also got this term here. So we talked about and or independently. We did not talk about and or as well as. So what do you think? What do 0.3, 0.4, 0.5 here indicate? The others can also try and answer. You can put it in the chat if unmuting is not an option. No? Okay. In the interest of time, let me start writing it here. So probability of A, that is damage due to high voltage. Yes, perfect. Okay, great. Thank you. So probability due to high voltage is 0.3. Probability of damage due to mishandling is 0.4. Now it says damage due to and or. So basically you're dealing with intersection as well as union. And we know that union is already taking care of the intersection area, right? So nothing to get confused about. This is simply union. So that is 0.5. And we know the formula. If we just rearrange it, this we can find if we calculate this thing. So it's 0.7 minus 0.5 and we get 0.2. Okay. That's it. Okay, great. All right. Next up, yeah, can be a slightly tricky question. Not necessarily, but let's see. So there are 10 actors acting in a play. So two of the actors, so two actors, one of whom is a male, are portraying hero characters. In total, there are 6 female actors. Let event A describe whether the actor is male, and event B describe whether the character is a hero. What is the probability that a randomly chosen actor is a male or a hero? Okay, so it's a lot of information, but let's start writing what we know. So we're talking about event A and event B, right? So let's say event A is male actor and B is hero. Okay. Now, what we know? So we know that there are 10 total. Okay. So out of the 10, we know that there are 6 female actors. So 6 female. So of course, 4 male. And then 2 are portraying hero characters. So 2 hero. Now out of this, 1 is a male. So we'll just say the other one is a female. This is the information that we know, right? Is there any other information that we can get from the question? Not to my understanding. Okay. Now, the question is, what's the probability that a randomly chosen actor is a male or a hero? Okay. So again, the person could be male, the person could be hero, the person could be male and hero. So just like the previous question, what we'll do is we want to find the probability of male union hero, right? And then what we can do is probability male. So again, same thing that we just wrote here, male, probability hero, and we can subtract. This is or, na? Yeah. So or this is going to be male and hero. Fine. So can you help me fill in these values? So probability of male, that's 4 out of 10, right? Probability of hero, so that's 2 out of 10. So this is right there, right? And male and hero, so that's just 1 out of 10. So this is 1 out of 10. So everything is out of 10, right? So now that is 5 by 10. Now that's 1 by 2. Cool. Okay. So it's not a difficult question. Again, simple union intersection, but it can appear a little complicated. Okay. Okay. 2 more questions to go. Just give me 1 second. Right. So an insurance company believes that people can be divided into 2 classes, those that are accident prone and those that are not. Their statistics show that accident prone person will have an accident sometime within a fixed 1 year period with a probability of 0.4. This is accident prone person. Whereas this probability decreases to 0.2 for a non-accident prone person. Okay, so basically people who are careful, people who may not be careful. Okay, now if we assume that the 30% of the population is accident prone, what is the probability that a new policy holder will have an accident within 1 year of purchasing the policy? So what category does this question fall under, that out of what we've discussed today? Well, if I'm solving questions, then it would very much become like your recorded lectures. So it's not being used to the fullest. I really don't mind solving them because I already have the solutions with me. But it'll be nice if you try, because even if it's wrong, doesn't matter. We're all learning here. Okay. I also solved these a couple of days back and I have the solutions with me written on paper so that I don't make a mistake here. But it took me some time to calculate these two. Okay. So don't worry if you're wrong. Okay, no problem. I can understand if unmuting yourself or typing is not possible. I completely understand that. But anyway, so I hope you've got a chance to read the question. So you've got some sort of conditional probabilities here because you're dividing your population into accident prone and non-prone groups, and then you're calculating some probabilities. Okay. So, so what we can do is we can also define 2 events. A can be accident prone population, accident-prone population. And B can be accident happening, like the accident actually happening, right? So of course, um, alongside that, we can have the complement of A, the non-accident prone population. Okay. So now what we know here is 30% of the population is accident prone. So probability of A here is 0.3. Therefore, probability of A complement, that's going to be 0.7. And then we know probability of accident happening for an accident prone person, that is 0.4. And we know probability of the accident happening for a non-accident prone person, that decreases to 0.2, right? So this is what we know. Now, what is the probability that the accident is going to happen? So we want to calculate this. Now, from what we've seen up until now, what we want to do is probability of B given A multiplied by probability of A plus probability of B given A complement. So this is basically multiplication, probability of A complement, right? This is same as what we had seen here in this case, right? So if these are two cases, this is A and B, this case plus this case, right? With A and without A, okay? You can plug in these values. So you have 0.4 into 0.3 plus 0.2 into 0.7, that is 0.12 plus 0.14, that is 0.26. Okay. Alrighty. Last question. An office has 20 persons in a group, and 5 of them are not fit to work for a particular job. If 3 of the people are selected at random and removed from the group in succession without replacement, what is the probability that all the 3 are not fit to work? Okay, so this is a slightly different question than what we've seen so far. You can do it a little bit manually. I'm not sure if it can fit any of the criteria. So of course, we're talking about the without replacement thing. But let's see, there's a simpler way. So all 3 are not fit to work. So basically, you can assume that there are 3 positions that you're doing. When you're selecting the first person, you want all 3 persons are not fit. So in the first case, there were 5 out of 20 that you could have, that would have fit the description. And when you did this, you're left with, you removed one of these 5 people, right? Then you're left with 4. And you're left with a total of 19 people. Then you're left with 3 people because you removed one of the non-fit people. And you're left with 18 people, 3 out of 18 people. So this simply is the answer. You can calculate this, but that simply is what the answer is. Okay. So again, some questions need not fit into a formula. I'm not sure if this would actually fit into one of these cases, but anyway, this is one way of doing it. Probability is not super simple to deal with. Sometimes you can get complicated examples, but I think the more we practice, the better it gets. So I hope these have given you an idea of what was discussed this week, and these would help you answer this week's questions. If you do encounter any questions that you're not sure of, well, of course, no solutions being discussed, but if you think that maybe the answers are not correct, or if you need some clarification, the best thing would be to put it in the Q&A, the discussion forum that is there on the course page, because there's a different TA who sets up the questions and is in charge of the grading and checking those. So even if you let me know, I will have to send it to them. So a quicker way would be, as soon as you have a question, you can directly go to the Q&A thing. Anyway, join the Q&A Google group, so that if you can see others having similar doubts as you. So that'll already sort out some things. In addition to this, so like I said, every Wednesday from now on, you would have your assignment deadlines, and every Thursdays you would have the assignment solutions being released. So 4 days ago, the solutions were released for week 1 and week 2. Like I said, the questions where multiple correct answers are there and maybe not all of them have been graded as right, or if there were no correct answers, those cases might take some time to reflect. So give another week, keep a note of it, don't forget about it, but give another week. If in addition to that, if any other question is there, then let me know. We don't need to go through the entire solution because you already have the solution with you. Let me know if there are any particular questions you would like to talk about. We can also do this later next week. That's okay, but just from the next week onwards. So for week 4, you would already have week 3 assignment solutions sent to you. So definitely take a look at that, and if there's any confusion there, make a note of the question, and then we can discuss it in that week. All right. If there's nothing to discuss today, then that's all for this session, for the third session. So recording is going to be uploaded. This PPT is going to be uploaded in the Google Drive. And this week's deadline is day after tomorrow, 12th. Don't forget that. And next Monday, we meet for week 4's live session at same Google link and same timing. All right. So I'll just stop sharing my screen now. All right. Thank you so much, everybody, for joining. I'll see you next week then. Bye-bye.